So, as the title suggests, this talk involves program transformations, and the most common contexts in which transformations are used are arguably compiler optimizations. So compilers take the input program, they run some transformations such as constant propagation, dead code elimination, and they produce an essentially equivalent program that runs faster or uses less memory. In essence, compilers use transformations to improve the dynamic performance of programs. So what's interesting and perhaps surprising is that program transformations have also been used to improve static program runs. And by that I mean they've been used to improve the results of static analysis. So as a first example, let's consider the constant propagation and folding optimization and simple parity analysis on the following program. So we set x to 3, we multiply by 4, store the result to y, then we again divide y by x, we should get 4, multiply this by z and store it to z. When we run parity analysis in this example, as expected, the analysis will conclude that x has to be an odd number, y has to be an even number, but it's interesting, z is unknown. And the reason for that lies in the semantics of the division operation. So if y is, say, 10 and x is, say, 5, then the result is going to be number 2, which is an even number. But if y is 10 and x is 3, then because on the roundoff, you're going to get that the result is 3, which is an odd number. But if you run the constant propagation, we're going to get the following program where the call to the division operation has been replaced with the number 4. Now, the parity analysis will easily conclude that z is an even number. So in this particular case, the transformation actually improved the precision of parity analysis. And what's interesting that some program verification tools such as SMAC and Seahorn use constant propagation among other analysis to transform the input program and then run the verification engine. As another example, let's consider conditional constant propagation and interval analysis on, again, a very simple program where we set x to 0, we say c is true, and then we run this if then else branch, or clearly only the then branch will be executed. Now, if you run the interval analysis on this program, you're going to get result that x has to be in the interval between 1 and 2, and clearly that's because the analysis has to merge the results from both branches. After we run the conditional constant propagation optimization, there is no such if then else command at all, and now the parity analysis, the interval analysis can easily conclude that x has to be 1. So what has happened here is that the interval analysis does not keep track of Boolean values, which is necessary here to infer that only the then branch will be executed. So again, we have the fact that the transformation improves the precision of an analysis. So Lagos and Fandry in 2008 actually observed that you can have the opposite effect. Now consider tree address code translation and a static analysis based on the difference bound abstract domain, whose elements are sets of constraints that keep track of the upper bounds on differences between two program variables. So the left-hand side, we're going to have a very simple program where we assume that x minus y is less or equal to 7, and the difference bound analysis will produce at the end of the program that x minus y has to be less or equal to 7, as expected. Now let's consider the translated program. So first we subtract y from x, store the result to t1, then to t2 we store the Boolean indicating whether or not t1 is less or equal to 7, and then we assume t2. So now if you run difference bound analysis on the translated program, you're going to get top. And the reason for that is that this is a tree address code, which means that we have commands involving three variables, and our abstract domain keeps tracks of relations between two variables. Also, this program involves Boolean values, which original program does not. So in this particular case, we had a transformation actually lose precision. So the reason why this is important is because some program verification frameworks such as Clouseau use tree address code translation to gain language independence. So in order to support several programming languages, they take the source languages, then translate them into an intermediate language. So these examples raise interesting questions. So if you have a transformation and semantics preserving program transformations, and those are the kind of transformations we're interested in, and we have an arbitrary analysis, how does this transformation affect the analysis? And can we explain this formally? Also, are there ways in which you can recover the loss of precision introduced by analysis? And lastly, what is really the real difference between transformation and an analysis? So in this work, we set up a mathematical framework and provide some basic results regarding these questions. So the key feature underlying our approach is that we take completely the semantic view. So programs are not syntactic constructs. We think of programs as transition systems. So in general, we're going to have source program S and a target program T that are identified by sets of states clearly some initial sets of states, and the transition relation delta, it's a binary relation modeling how programs execute state by state. On the other hand, we'll not think about program transformations as syntactic changes. So we'll be interested in those transformations that can be modeled as bisimulations. Essentially, this is a semantic model of transformations where bisimulations are proofs that these two programs are semantically equivalent. And when I say semantic, I mean observationally equivalent. For instance, their input-output behavior is the same. So one appeal of using biosimulations is that we can essentially formally compare invariants on two different programs. So far, I've been comparing program on the invariant on the target program with the invariant on the source program. And intuitively that makes sense, but formally it might not, because source and target program might use different program variables, they have different locations, so the invariants might be in principle incomparable. So it's nice about biosimulations that they give us a formal way of comparing invariants on two different but semantically equivalent programs. So if you have a target program T and we have some inductive invariant H on this program, we can compute its image in the source program based on this biosimulation using the post operator, and it's a known result that this propagated invariant is also an inductive invariant for the source program. So likewise, we can have an inductive invariant, let's call it G, on the source program, and we can compute its preimage on the target program, and that preimage is also going to be an inductive invariant for the target program. So in this work, when we say that H is stronger than G, what we really mean is that if you propagate H to the source program, that has to be more precise than G, or when we propagate G to the target program, it has to be less precise than H. The real reason why we use biosimulations lies in the fact that they are witnesses to correctness of program transformations. So if you go back to our example with the if-then-else branch, an excerpt of the biosimulation witnessing their observation equivalence is as follows. So we're going to say that the state after the first command in the target program is matched with the state after the first command in the source program if and only if the x and x prime are 0. We're going to have the same requirement for locations for the second command, and we're also going to require that c and c prime are true. And lastly, we're going to also require that states after the command x assigned 1 in the target program match the locations of the then branch in the source program. Now, as biosimulations capture the reason why transformations are correct, we can see that they really provide useful information about semantics of these two programs. So, more precisely, if we go back to the results of interval analysis on these examples, we know that the source analysis was imprecise because it was not able to keep track of the Boolean information. But this is precisely the information that's been captured by the biosimulation. So a natural hypothesis to state or questions to ask is, do biosimulations explain loss of gain precision introduced by program transformation? And the answer to this is yes. So the main result that we show in this paper can be informally described as this. So we have a target program T, we have a source program S, we have an inductive invariant on the target H, which we computed with some abstract domain, and we also have some invariant on the source program G, computed using the same abstract domain. So if H is stronger than G, what we do, we formulate several analyses that work exclusively on the source program, and they utilize the biosimulation B. And those analyses are more precise than the propagated H. Now, since these analyses are completely defined on the source program and biosimulation, indirectly, biosimulation captures the precision gain introduced by transformation. Now, if H is weaker than G, that means that G is stronger than H. So by duality of biosimulations, then we can simply essentially reverse the role of a source and target program and also explain the loss of precision. Now, one of the analyses that we introduced in the paper, and I'm going to get into more detail in this talk, is the biosimulating analysis. So the key idea is very simple. So we're going to run the source analysis by running the target analysis. So we'll be using the biosimulation to jump back and forth between the two programs. So one iterate of this biosimulating analysis looks as follows. So we start with some abstract state on the source. We jump using the biosimulation to the target program. We pick up all the useful information the biosimulation provides. We make a target analysis step there, and then we jump back. To see why this is so powerful, I think it's best to see on an example. So I'll again be using an example with a tree address code translation. So On the left, again, we have the code, the original code. On the right is a translated code, and here is the biosimulation. So if you remember the original example, we know that the actual analysis on the transform program is actually less precise. So the first thing I'm going to do, I'm going to show that the biosimulating analysis can actually, in this example, match the precision of the original analysis. So, and I hope this is going to work now. So the first thing that an analysis does, it starts with some abstract state, and it jumps to the target program and picks up all this useful information for the biosimulation. However, this information does not imply any useful difference bounds analysis. So the analysis makes a step, and basically that gives nothing. It gives stop, as we already saw, and then basically again jumps back to the source. After some time, the analysis will jump just before the assume statement. It will pick up the biosimulation information, but this information again does not imply any useful difference bound analysis. Then again we're going to make a step, and that's going to produce stop, as we already know. But now comes the key point. Now the analysis again has to jump back to the source. It has to pick up all this useful information, such as that x has to be equal to x prime, y has to be equal to y prime, and so forth. And if you look carefully, this information implies that x minus y has to be less or equal to 7. So the biosimulation sort of states this in this particular case. Now, what we can do, because of the duality of biosimulations, we can invert the roles of source and target, right? So now we can essentially analyze the target by analyzing the source. So again, we can start with some state here. We're going to jump here. Then you're going to do analysis, and sorry, let me go back. Okay, so we're going to do the step, and we know that the source analysis gives that x minus y is less or equal to 7. And then when we jump back to the translated code, we're again going to pick up useful information such as that x is equal to x prime, y is equal to y prime, and clearly that implies that x prime minus y prime is less or equal to 7. So again, the biosimulation information enables us to transfer really powerful invariants from one program to the other. So what's interesting is that utilizing this biosimulation information corresponds to techniques that Logos and Fenrich in the original paper introduced for counteracting loss of precision introduced by tree address code translation, and in turn they use some techniques introduced by Minet. So more formally, we're going to have a source program S, we're going to have a transform program T, and we're going to have a biosimulation witnessing the semantic equivalence between the two programs. So we're also going to assume some program agnostic abstract domains such as octagons, polyhedra, intervals, and so forth. And we're not going to keep track of, we're going to carry around Galois connections. So we're going to stay within the concrete domain. So you're going to use the closure operators to define abstract elements of the abstract domain. So in these closure operators are, as expected, monotone, increasing, and idempotent, and they're called CLS and CLT in this particular case. And we also assume we're given an abstract transformer for the abstract domain for the target program. So now I would like to just stop and explain that this actually fits the practical setting. So program verification frameworks anyhow run the transformations. So they had the source program, they had the target program. So the biosimulation can be generated by these verification frameworks as evidenced by a lot of work in the areas of credible compilation and translation validation. So compilers can essentially generate the biosimulation information. They have all the necessary information to do that. So, and also, abstract domains are available just as is the abstract transformer on the target program. So sometimes the abstract transformer for the source program is not available, such as in program verifications frameworks such as Clouseau that are language independent, but they always have the abstract transformer for the target program. So the actual transformer looks as follows. So we start with some x, which is like it is just jumping, so I'm going to explain piece by piece. So we start with some set of state x on the source. We jump to the target program. We make sure we stay within the abstract domain we chose. We make a step. We come back, and then again we make sure we stay within the abstract domain. So the main result we can show is that if G is an invariant on S computed with the abstract domain we chose, and if G prime is an inductive invariant computed using the biosimulating analysis, and if you have H, which is inductive invariant on the source program T, then if H is stronger than G, then G prime is more precise than propagated H, which is more formally formatted as this. So in the paper, we have other two analyses that we formulated on the source that use biosimulation, and those analyses are of more theoretical nature, but what's interesting about them is that they are defined in terms of combining the biosimulation and the original abstract domain. So basically, we formulate a new abstract domain that can intuitively be thought as a product of the original abstract domain and the biosimulation relation. And also in the paper, you can define discussion and widenings. So at the end of this part of the talk, I can kind of conclude that we show that biosimulations can capture the loss of gain of precision introduced by transformation. So, but we also were interested in what is really the difference between the analysis and the transformation. And to make more clear what it means, I think this is best understood through an example. So we know that on the transform program, if you run the parity analysis, you're going to get a more precise result than on the source program. What's interesting is that we can match the precision by running a very simple analysis on the source program that does not involve biosimulation whatsoever. So we can use essentially the product of constant domain and parity domain. So in parallel, we can compute the constant information and parity information, and then when we're doing the analysis for the parity domain, we can use the information from the constant. So for instance, when we analyze the y divided by x, we know that the constant analysis will spit out that's 4. So then we can use 4 to refine our top and get that z as an even number. So more formally, we could match the precision of the analysis on the transform program with a simple one-way reduced product of constant and parity domain where information is shared from constant domain to the parity domain. Now, this raises a very natural question. So if I have so let's say a complex analysis, can I break it up into a transformation followed by a simpler analysis? So the answer to this question is yes. So this is the way we construct such an analysis. So we assume that the reduced products analysis is being done over two domains, C and D, that are again given in terms of closure operators CLC and CLD. And the reduced product analysis works as it makes a step for the domain C and produces result X, it makes a step for the domain D, produces Y, and then refines Y with information from X using this reduction function rho. So rather than doing the fixed point over this method that I just described, we propose something else. So first thing that we propose, compute an inductive invariant using the C abstract domain. I'm going to use that invariant to transform the program S to a program T. But when I say transform, I don't mean a syntactic transformation. I mean more a semantic transformation. So basically, we're going to generate a new transition relation for the target program that is a refinement of that of source. Sorry. It's not the best thing. Sorry. So basically, we require that all the states in the target program has to satisfy the inductive invariant I. And then we run the analysis using the abstract domain D on the target program. And we prove in the paper that that's actually more precise than running the one-way reduced product on the source program. So in conclusion, in this paper, we show how biosimulations can capture the loss of gain of precision introduced by program transformations, and we formulate several analyses that utilize biosimulation information and show this. So one thing that we would like to point out that we were very interested about is phenomena, and at the point of this work was to set up a way of thinking about this problem and some initial results. But there are several very interesting open problems. For instance, if we have a program transformation and we have some abstract domain, can we automatically conclude whether or not this transformation will introduce precision or will lose precision for every program? Or what is the class of programs for which this will be the case or not? Also, it would be interesting to run, let's say, biosimulating analysis in program verification framework to see if we experimentally evaluate this analysis to see if we get better results than with the current tools. Also, people have been designing program transformations with the goal of improving the runtime performance of programs. Now the question is, can we design program transformations with the sole purpose of improving the static performance of programs? And there are plethora of other questions that we can discuss offline. Thank you.
Thanks. Questions?
Yeah, sorry for this thing. I thought it was going to work better.
That was pretty good.
Okay.
There's another one coming. It's better.
So you use the closure operator. You use the closure operator induced by an abstract domain. So you need abstract domains which have an abstraction.
Yes.
You mentioned also the polyhedral domain that does not have.
So yeah, so basically what I wanted to say is that we assume program agnostic abstract domains. Because essentially if we have an abstract domain, we want to define in terms of closure operators. They work on the concrete states, right? But we have concrete states of the source and the target program. Now, they may be different. They involve different variables. So that's why we assume we have an program agnostic abstract domain which we can lift to a program-specific abstract domains using disclosure, CLC and so CLS and CLT.
Yeah, that's okay. But
yeah.
My point is that you mentioned also the polyhedral domain that does not have a closure operator induced.
Oh, okay, then that was my mistake.
Oh, okay.
Thank you. Thank you.
And the second comment is if all this stuff can be related in some way to complete the completeness notion of program analysis.
Yes, we looked at actually all papers which were in model checking, right, and strong preservation and relating this to the completeness of abstract interpretation. We are aware of this connection, but we have not formally investigated it yet. But it's like I said, like the whole point of this is really to provide a formal way of thinking about this problem. And there's really plenty of other questions to ask, and one of which is that question.
I have your post and pre. Why do you take pre and not pre-tilde?
And not what? Sorry.
Pre-tilde.
WP.
Not pre or not.
It's just a choice that we used. There was no particular reason, I guess. I guess, yeah, they resemble, I guess, model operators. That's the way my co-authors devise these names, but they have a very simple definition, just to take all the states that can take it with biosimulation. Yes, but I think you can do the weaker speculation.
You work on transition systems, right? So
it's more natural. Okay.
And I have another question on functional programs.
Okay.
It's vaguely related, but there are 2 points. I know a paper by David Sands where there are some transformations that do not preserve termination, but they preserve partial correctness.
So, okay.
And I have another one, which is when you do strictness analysis and you do continuation passing style.
Okay.
It always improved the analysis, but it was in a fine bounded domain, ascending chain condition, and then it becomes unbounded.
So, okay, maybe just start top bottom. So, like I said, one of the open questions is that if you have a transformation, and if you have, let's say, an abstract domain, and you want to do analysis, can you prove that this transformation will always improve the precision? So it's an open question, and I don't know what else to add to that point. The other point regarding the non-termination, so let me try to answer it a little bit differently. So we are aware that there are some transformations that compilers do that are not biosimulations. So for instance, in C, there are a lot of operations that have undefined behavior. In a sense, you can do whatever you want. So it's non-deterministic, and then the compilers pick one particular choice. Now, that might not, if you want to prove the semantic correctness using biosimulations, it's not going to work. So the only thing you can do is use simulations. So in that case, our actual theoretical results do not transfer to such cases, but we believe that the overall idea of using the simulations to kind of jump back and forth holds.
Any further questions? We still have some time if you want. Yeah.
So your result that connects reduced product and transformations. It's on one of the last slides.
Yeah, let me use this. Is this one or even before?
Yeah, this one.
Okay.
So does this mean now that the notion of reduced product is obsolete? We
No,
can just-
absolutely not. So first of all, this is one-way reduced product. So
It's what?
it's a one-way reduced product. So the information is shared only in one direction. So if you have, a classic reduced product, you cannot apply this. At least we don't know how to apply these techniques. I'd be very surprised if you could do this. So this is a one-way reduced product.
So the final result that says more precise than product analysis, like
Better than one-way reduced product analysis.
like always more precise
Always
on any
i-
program. I mean, like there's
Yeah,
must be
so
cases where
we assume one particular form of a transformer that's kind of pretty common for the one-way reduced product analysis.
I see.
So it's not the most general one, but it's pretty common.
Mhm.
And for all those classes of absent transformers, this holds. It's a very general
Is that
theory.
a strictly more precise? or-
It's not strictly. It's not.
Okay.
It's subset inclusion.
yeah.
But it can be strictly more
It can be.
Mhm.
It can be. So yeah, we were not able to show exact equivalence. We don't have examples where it really is more precise, but we could not. This is the best we could prove.
So this answers my second question,
Mhm.
which would have been, can you go back? So when you have a transformation, can you say that you have an equivalent use of the reduced product?
You mean what are the
I mean,
conditions?
this directed use of the reduced product, right? So that's for every transformation. I mean, instead of doing the transformation and the analysis, just do the
Reduced
no.
product.
Yeah.
So yes, I'm not sure in what scenarios would you like to do that, but so maybe this will answer my question. So one on Patrick's paper, he showed us syntax is essentially an abstraction of semantics, right? So you might have a semantic transformation that I introduced on the following slide, but clearly you need to implement it somehow. And if you want to implement it in the level of syntax, you might introduce imprecision. So this is maybe what explains that more precise. This is, again, transformation on the semantic level. So if you go over to implement it, you'll introduce some over approximation.
One more.
And if I understood well from your previous answer to Patrick's question, it's key that you use a bi-simulation relation.
Yes.
So there are a lot of alternative behavioral equivalents well known in concurrency. So for example, simulation equivalence, stuttering equivalence, weak bi-simulation, and is really a key point to use bi-simulation, or?
Yeah, so we allow biosimulation. I think the results also hold for stuttering biosimulations. But yes, we do require general notion of biosimulation. So it's a simulation and its inverse is a simulation. So that's basically a definition of biosimulation.
But you can pick the transition system, right? I mean, for example, when you do block encoding, you could just use a transition system where you forget some control points.
Okay.
No, I'm just wondering.
So okay. So what you're saying in that case, you would not have a biosimulation?
No, you could. You could still get a bisimulation because you're allowed to choose a transition system, and so this is why you can choose a bisimulation.
Yes, and in general, the biosimulations are sufficient to preserve observational equivalence. So even though the target program might have, let's say, less actual computations, so the actual observations that it produces are going to be the same as the target program.
Yeah.
Next slide. Next slide.
Next slide.
Yeah.
We're going to go slide by slide.
yeah.
No, that's fine.
Okay. Yes. Why don't you have to take a fixed point, because you have one analysis that improve the other and the other that improve the first?
Okay.
And why is it stable? Is because bisimulation is only on one step, or?
So can you repeat the question? I didn't hear you.
First by the second by the third. You could, in general, you have to take a fixed point to have the best of the two worlds.
Yes.
In the reduced product.
Yeah, exactly. That's yeah.
And you don't have it here.
Yes, we
So
don't have
why?
it. Well,
Because it's one step computation? Or
So what you're saying is that in reduced product analysis, you do the transfer information in every iteration, right?
Mhm.
And here you don't. You first compute the whole invariant for the program, and then you transform the program. So I don't know the answer why. I know it holds because we've proven it. My hunch is that once we compute this inductive invariant, we essentially push it into the program. Because you see, delta t, which is a new transition relation, it only works over the states t that satisfy the inductive invariant.
Yes.
So basically, if you run d on t, it's going to pick up everything that the previous analysis inferred.
But you could do the transformation on the fly using what you have
Yeah.
done.
We have not thought about doing transformation on the fly. Yes, so it's,
Because your true example, the true can come from some analysis, and you do the transformations, and you go
so
back.
basically, you would, in each iterator of the fixed point, you would do transformation.
Yeah.
Yeah, we can talk about this more, but
Okay.
this has not crossed. This has not crossed my mind. This is a little bit too extreme for me at this moment.
Patrick, Zvonimir, you're both at NYU. You can
Yeah, exactly.
All right. Thank you for answering all these questions.
Thank
I'm
you.
not running away.